Hello class. Today we're going to finish up chapter 18 on thermodynamics. The focus of today is Gibbs free energy in non-standard conditions and then the relationship between standard Gibbs free energy and the equilibrium constant. So I think the thing to think about at this point with Gibbs free energy is you're going to take these reading problems and you're going to focus on the which equation are you going to use. So what we have is we've talked about Gibbs free energy in terms of the direct method and the indirect method, and we've talked about Gibbs free energy in terms of delta H enthalpy and delta S entropy changes. Let's see what's going on here. I'm having a little problem with my pad. There it is. All right. So what you need to be thinking about is you have this equation, delta G equals delta H minus T delta S. So that's one way to solve for Gibbs free energy. And the other one is delta G equals the summation of the number of moles of delta G formations of the products minus the summation of delta G of formations of the reactants. All right. And so, and then we had the indirect method. So just keep that in mind. That's kind of like a Hess's law problem. All right. So indirect method. And then the other thing that comes out of this is that can you define standard Gibbs free energy of formation? We're at 25 degrees Celsius, 1 atmosphere pressure, 1 mole. We're making the substance from its elements, and we're making 1 mole of that substance. So it's very restrictive. Also, change in Gibbs free energy of formation, or standard Gibbs free energy of formation, is 0 for elements in their standard states. And again, how do you know they're standard states? You look at the periodic table. Things that are in black on the periodic table are solids. Things in red are gases, and things in blue are liquids at room temperature. And then knowing that carbon graphite is the allotrope of carbon at 25 degrees Celsius instead of diamond. So those are some of the things that we've picked up on. So again, a lot of times we're dealing with non-standard conditions. So again, only when the reactants and products are in their standard states. Their normal state at room temperature, 1 atmosphere pressure, 1 molar concentrations. Anything outside that, we're going to be solving for delta G. All right. So here is the equation. You're going to memorize this equation. Delta G, non-standard conditions, is equal to the standard delta G plus RT ln of Q. And again, we see Q again, the reaction quotient. We have to know what the concentrations of the reactants and products are at equilibrium. Or not at equilibrium, non-equilibrium conditions. Then we'll talk about at equilibrium K here. All right? Because what happens is, at equilibrium, delta G is equal to 0. So it's neither spontaneous in the forward or reverse direction. And so then when we solve for standard Gibbs free energy, we get negative RT ln of K, the equilibrium constant. The R that we're using is 8.314 joules per mole Kelvin. Makes sense because when we look at delta G or delta H, it's generally in kilojoules per mole. So we don't need the liter atmospheres mole Kelvin. We need the joules per mole Kelvin ideal gas constant units. So some more memorization here, and then once you memorize these equations in purple, then what you can do is you're going to read the problem, determine which equation you're going to use to solve the problem. All right, so let's look at a problem here. It says calculating the standard Gibbs free energy for the reaction under non-standard conditions. So we have the reaction at 298, and we have the standard Gibbs free energy of negative 71.2 kilojoules per mole, or just kilojoules, and they want us to calculate the non-standard conditions. All right. So the first thing that should come to mind here is delta G, non-standard conditions, is equal to delta G naught plus the RT ln of Q. All right, so that's what we need. Other than that, it's really just plugging it in, right? I mean, what you have here is this goes here, and R is 290, or T is 298, and R, you know it already, it's 8.314, and you could say, I mean, maybe you want to make this times 10 to the negative 3 kilojoules per mole Kelvin. I don't know how they're going to do it, but I mean, by doing that, everything's going to be in kilojoules. That's the whole thing. Everything has to be in kilojoules or kilojoules per mole in order for this to work. And then Q, all right, well, let's go on and write that down since we've got it here. So Q, the reaction quotient, is equal to products over reactants. So we got 2 moles, 2 atmospheres here. So we could say 2 atmospheres squared divided by 1.0 atmospheres squared. And then we have O2, and for O2 we have 0.1 atmosphere. And that's to the first power, so we're not going to worry about that. All right, so there it is. So we're going to solve for Q here. So you know how to do that part. That's nothing new. We know reaction quotient backwards and forwards. All right, let me erase all of that so you can follow the process. Okay, so they solve for Q first. That's fine. And same thing. 2 over 0.1 squared, 2 squared over 0.1 squared times 0.1. Here's Q. So Q is 4 times 10 to the third. Okay. Notice they do use the old law of mass action. Law of mass action. So when we talked about stoichiometry, or equilibrium, we talk about law of mass action. All right, so here it is. They converted everything to joules, and that's fine. I don't care which way you want to do it. So they changed the 71.2 kilojoules into 71.2 times 10 to the third joules, because kilo means 10 to the third. Then we have 8.314 joules per mole Kelvin times the temperature, 298 Kelvin times the ln of Q. And you plug that in on the calculator, and I just plug it in just like you see it. I don't think you really have to make it 2 different terms here. I think you could just bam, 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 bam through that. You should get negative 50.7 times 10 to the third joules, and then they converted it to kilojoules. So that's why I tend to go to kilojoules right off the bat, is so that I don't have to do that conversion at the end. But what you should get out of this is that under these non-standard conditions, this reaction is still spontaneous. All right, it's not as spontaneous as it was. So that tells us that these non-standard conditions are not as supporting the reaction going in the forward direction, right? So this is just saying what you could look at. Let's go back to that reaction again. Let's see. I want to see what that. So what they want you to do here is to say that it's less spontaneous. So therefore, that's a big jump there, but it says the calculated results is consistent with what you expect based on the Chatelier's principle, increase the concentration of the products and decrease the concentration of the reactants relative to the standard conditions would make the reaction less spontaneous. So you could, I guess, infer that from your new calculator, your new value there. All right, here's another one. I'll let you do that one. Same process though. All right, so let's look at, this is an important concept because it ties in together all those chapters we dealt with equilibrium. And what we know about equilibrium, the larger the K value, the more the reaction went in the forward direction. And so that would generally indicate, if we have a huge K value, that the reaction spontaneous in the forward direction, non-spontaneous in the reverse direction. So we need to relate thermodynamics to equilibrium, or the law of mass action, if you want to think of it that way. So at equilibrium, delta G, non-standard conditions, is equal to 0. So if we manipulate the equation, delta G, let's write that up here, delta G equals delta G naught plus RT ln of Q. Now we're under equilibrium conditions. This delta G equals 0, and we're solving for this. So that's why we get delta G equals negative RT ln of K. So when K is less than 1, then the standard Gibbs free energy change is positive, and the reaction is spontaneous in the reverse direction. And that makes sense, right? K less than 1. We know that if K is less than 1, the reactants are favored over the products. And so delta G is positive, and we have a non-spontaneous reaction in the forward direction, spontaneous in the reverse. If K is greater than 1, then standard Gibbs free energy is negative, which means spontaneous in the forward direction. And if K equals 1, then standard Gibbs free energy is equal to 0, and you have chosen the reactions at equilibrium. You've chosen, the values make the reaction at equilibrium. Now, you should spend time looking at these graphs, because this shows you the relationship of graphically between K and delta G. So here we have A going to be in the top left, A going to be, K is less than 1. So what you know right off the bat, if K is less than 1, the reactants are favored over the product. So over here we have, on the left-hand side, we have pure A, and over on the right-hand side we have pure B, and the energy well is lowest closer to pure A. All right, and so what this is showing is the relationship is that this reaction is non-spontaneous in the forward direction. You can see it has to go up the hill. It's not going to happen. And it's easier for it to start from pure B and roll down the hill, so it's spontaneous in the reverse direction. So this is when we have a small K value and we have delta G is actually positive. All right, for the next one, we have a large K value. Okay, then we have a lot of reactant goes to product, and the energy well is closer to product than it is to reactant. So again, easier for the ball to roll down the hill, if you want to think of it that way. So it's delta G is positive in the forward direction. Delta G is negative, but it means that it's spontaneous in the forward direction. Let's say it right. Oops. And then the next one, the last one here, where it happens to be K equals right at 1. All right, at equilibrium, we have a nice parabola here, and the lowest energy well is right in the middle. Now, again, not likely. That one's not as likely as the other ones, but it does happen. But again, look at these and kind of think about how that works. Is that when K is greater than 1, that means the products are favored over the reactants. So that's why we're seeing K moved over here, on the right upper one, you see that the energy well is closer to pure product than pure reactant. Same thing, K less than 1, that means reactants are in greater concentration than the products, and that makes K less than 1. All right, so this problem says use tabulated free energies of formation to calculate the equilibrium constant. All right, so this is what I'm talking about. When you read a problem, you're going to think about, well, which delta G equation do I need? Well, we don't have delta S, so that equation's out. We don't have multiple chemical equations here, so we're not doing the indirect method. And they tell you, use the tabulated free energy. So we're using the direct method of calculating delta G for the reaction. So we look at the standard Gibbs free energy of formations in a table for the dinitrogen tetroxide and the nitrogen dioxide. And we plug those into the direct equation. All right, so the direct equation, you need to, again, have that memorized. And again, we've seen this same equation for enthalpy and entropy, so it's not that difficult. And again, you have only one product, so that's nitrogen dioxide. So 2 times the, I don't like how they did the bracket here. I would have put the bracket on the outside the 2, put it like that, but I think that's a typo. Minus the standard Gibbs free energy of formation for the dinitrogen tetroxide. Plug that in, we get 2.8 kilojoules. 2.8 kilojoules for this reaction. So, non-spontaneous, right? It's a positive value. But we still can calculate the equilibrium constant. So what you know is, because this is 2.8 and it's positive, you know that the reactant is going to be favored over the product. All right? This reaction is non-spontaneous in 4 directions, slightly, but it's not, so therefore we know the reactant should be favored over the product. All right, so now let's use this to calculate the equilibrium constant. So here's our equation. Standard Gibbs free energy of the reaction is equal to negative RT ln of K. We know what delta G is, so we're going to solve for K. So first of all, we divide by negative RT. And so that gives us delta G reaction over RT negative. And now we got the ln of K. We plug in our values. We get a number of negative 1.13. And then we say K equals the natural exponent of negative 1.13. And we get 0.32, which is 3.2 times 10 to the negative 1, which says that, yes, the reactants are favored over the products. All right? So you can try that again. These aren't difficult problems. They're just reading the problem, deciding which delta G you have to have. All right. If we combine these 2 equations, you can get a line equation. And the slope of the line is equal to negative delta H, standard enthalpy of the reaction, divided by R. So there's my slope. The x-axis is 1 over T in Kelvin. And then the y-intercept is the standard entropy change of the reaction divided by R. I'm not as interested in this equation. I'm not going to test you on it. I think it's a little bit much for this class. This would be more for when you take your thermodynamics course as an engineer. You may focus on that a little more. I'm not really interested in that equation as much. Well, that concludes Chapter 18, Thermodynamics. The main things, again, are you've had enthalpy from a previous chapter in Chem 170. We've talked about entropy, that entropy is a driving force for chemical reactions to occur. We looked at the relationship between entropy and the enthalpy change of the reaction divided by temperature, and we saw that if it's at high temperatures, then it doesn't make as big a change on entropy. But at low temperatures, a temperature change does affect entropy of the surroundings. And then we said instead of dealing with all of that, we can talk about it in terms of free energy. And so we came up with delta G, or Gibbs Free Energy. And then we looked at multiple equations using delta G, or standard Gibbs Free Energy, to solve for that. And so the last part was to look at the relationship between Gibbs Free Energy and standard Gibbs Free Energy with the RTLN of Q, and then also standard Gibbs Free Energy and equilibrium, and to look at that relationship. So that's important. Bottom line, theoretically, what you want to think about is the reaction's got to be reversible, and the heat can't be lost in order for this to work. If the heat's lost, the reaction's not reversible, right? So that's the problem with, like, when we burn fossil fuels in our car, the heat's lost, so that's not a reverse. You can't just force carbon dioxide and water through the tailpipe, goes through the engine and recreates gasoline, right? It doesn't happen. So that's the kind of thing that you do get out of this. That's the theoretical part. But I focused on the calculations because I find that's what students have the most trouble with. And the theoretical part, I'm hoping you're reading the book, and if you're not understanding a concept, you'll email me and I'll talk about the concept theoretically, and then again show an example or give you a real world example. Hope that helps. Just make sure you understand delta G and focus on it, because that's what you need in order to be successful in electrochemistry. So the main things coming up in chapter 19. You need to go back and look at your oxidation reduction rules. Make sure you know those. So look those up. There's a table in the book about oxidation reduction rules, and they are hierarchical. So that means rule number 1 takes precedent over all the other rules, rule number 2, and so forth. So make sure you know your oxidation reduction rules. Make sure you understand delta G, because what we're going to look at, and we kind of saw a hint of it in this chapter, we're looking at electrons, and the electrons are going to be flowing, and we're going to be able to use delta G to determine electrochemical cell potential, or how many electrons are flowing and so forth. So you have to master 18 in delta G and redox reactions and oxidation reduction rules, or oxidation and reduction states or numbers, in order to be successful in chapter 19. I hope that helps. And again, if you need more help, just email me and I'll be glad to either make a video or respond through text. Thank you.